Dollar store versus pound shop LED lamps, and this video was inspired by another channel, Adrian Black's channel, and I shall put a link to the very video down below in the description where he took apart a dollar store lamp. And I was thinking, it's going to be the same as a typical Poundland lamp. I'm sure they're all just made the same style, but his was completely different. It made me wonder, has something changed in the lamps here? Is this the evolution of the lamp? So let's take a look at Adrian's lamp first. It's based on the standard aluminium substrate circuit boards. You can see from the fact I've turned this over that things are not the same. But it's the aluminium substrate circuit board where it's a thin piece of aluminium with a layer of fiberglass and then the layer of copper, and then it's processed, and then it's sort of this solder resist is put on, the white solder resist. And the idea of that is that these circuit boards are very good at absorbing the heat from the LEDs and spread it across. And in the case of this one, and well, in the case of Adrian's as well, it's got a metal cup inside, an aluminium cup, and when you put this circuit board in, it's physically pressed in to the point that there's a friction fit between the aluminium disc and the cup here, and that helps spread the heat along the whole body instead of just relying purely on the disc itself to dissipate the heat. Interesting things to note about Adrian's circuit board here. It has two connectors on it. The connectors actually stick through the aluminium substrate just to provide separation so connections can come through from the back. You get the mains connection coming through, and it's going straight to a bridge rectifier. The output of that then goes to an electrolytic capacitor in the back, which is also plugged into this little one-way sort of friction fit connector. I'm guessing that's for two reasons. The electrolytic capacitor, they want to keep it away from the heat, although it is effectively still being baked inside that little container. But also the high voltage electrolytic capacitors, like the sort of 250, 400 volt ones, they tend to be the sort of standard case with the pins sticking out, I'm guessing, and it just means they can shove it in to actually use. And it also probably means that they can change the capacitor value depending on the type of lamp as well. There's a 105, that's a 1 megohm discharge resistor. That's the one that goes across that capacitor to make sure the lamp goes out in a nice, decisive manner. And after that, the only other components are a little sense resistor here, and they've got two positions to the sense resistors, and then one of these current regulator chips. And these are the chips that basically act like a resistor. You can see all the heat sinking around it to try and take the heat away. And they sense the current flowing through that resistor, and as soon as it reaches a certain voltage across it, they start regulating the current back. So even if the mains voltage fluctuates up and down, this will just keep a constant current. And these have the other advantage that if the thing starts overheating, then this detects the temperature as well. And if it gets too high, it will protect itself by just nudging the current down until it gets to a nice equilibrium point. So this lamp, I think that was a 10 watt lamp in Adrian's video, and it was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 LEDs. I noticed they're actually numbered. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Interesting. So I went out and bought a lamp thinking, well, it's a very similar case. Have they changed it in the British ones? And it turns out that the circuitry in the British ones, the last time I looked inside some of these, it was a little buck regulator. But now they've gone back to what they used to use before, and it's the capacitive droppers by the look of it. But I've not opened this one yet, and this is a 10 watt one, and I got so far with this. So let's actually focus on something here. Let's bring the focus up a little bit. I decided to investigate these anyway. I got a few of them to open up, and part of the thing that's evolved in these is the multi-chip LEDs. So that's how they can ultimately use the capacitive dropper, because it means that they can have a much higher power lamp for a given value of capacitance. And it's interesting, this one has a little auxiliary circuit board that has gone through those same push-in contacts that keep it away from the aluminium frame. And ultimately means that the little power module at the back with its electrolytic on board, and it's a fairly beefy capacitor. I think it's an unusual value. It's 920 nanofarad, 400 volt. It means that they can just plug that module onto here. This circuit board also, I'm going to bring it up. I'm going to focus up close like this. And I'm going to zoom in a little bit, because this thing has some interesting quirks. Do you see how there's 3 LEDs missing here, but there's another one in there? That LED in there bridges out the three positions. So they can adjust down. If they want to remove 3 LEDs from this circuit, they can put a wire link across there, a little surface mount link, or a low value resistor. If they want to just remove 2 LEDs from the circuit, they replace the 3 LEDs here with 1 LED, and that means there's 2 LEDs less. On the other side, where you've got that little pad there, that is bridging these 2 LEDs. And what that means is that if they remove those LEDs and they put one of them across here, it would remove 1 LED, but if they put a link across here, it would remove 2 LEDs, although at that point the circuit board would be quite dark at one side. It just means they can use the same circuit board for multiple wattages, I guess. Let us go back down to here. That's looking pretty good. Let's unbox this lamp. The other thing I haven't done actually is open this. Let's see if I can get this out, because the circuit board didn't come out too easily. It is wedged down a guide in here. Let's see if I can not lacerate my fingers in the process. I think that's kind of trapped in. Where's a sharp blade? Let's bring in a sharp blade and just try and lever this off at the risk of lacerating myself in the process, or snapping the blade. Okay, let's liberate this contact from the back. This is one of these push-in contacts that they basically thread the wire through, and then they pop this little rivet in. It's the end contact, and it traps the wire. Is this going to make it easier to get out? A wee bit easier, but there's still a wire trapping that in on the actual housing here. I shall try and work out which one that is. I shall try. It's pretty tight in there. Am I going to be able to do it? I don't think I am, actually. I could faff around for ages here. Nope. It's quite tight in there. One moment, I'll keep giving it a go and see if I can get this out. Ugh. And if it's not going anywhere soon, I shall give up. I shall use brute force and ignorance. That's probably the best bet. Let's just grab this circuit board, a pair of pliers, and pull it. There we go. That's better. So there is a component. That looks like a typical, often in these they'll use a 10 ohm resistor. Let's bring the meter in. Let's turn it round to the 200 ohm range. And check that. And it doubles up as it limits the inrush current, and it also acts as a fuse if something goes horribly wrong. Is it going to be 10 ohm? I'll just hold one of the fingers. It's not going to affect the reading too much. Assuming I've not broken this resistor with brute force. It's 10 ohm. Okay, so that's a typical 10 ohm fusible resistor. The value of the capacitor is 1.1 microfarad. That's quite high. Okay, so that's got me intrigued now. I want to know what's in here. So let's get this lamp out, because this is probably one of the highest power lamps they do, rated 10 watts. First of all, let's test it. So I shall bring in the rather fetching pink lamp holder. I shall plug this into the hoppy, and we'll bring the hoppy in, the flickery hoppy, and we'll screw this in and see what sort of power. It's not mega, it's bright enough. 10 watt on the, oh, look at that. Literally 10 watt on the button. That's really impressive. Power factor 0.6, which is fairly typical what you'd expect of any sort of electronic supply. 65 milliamps, and pretty much 10 watt on the button. That's very, very impressive. Okay, let's open it up. And this is where I have to say that the plastic in these, I'm going to give it the tooth test. No, I don't need to give it the tooth test. It's flexible. You can actually crush it in with your fingers. It's the ideal way to make your own custom lamp. In fact, let's power it up again now I've done that. Ugh. Let's get that socket up again now that I've fashioned it. I could sell them on eBay as art. Iceberg lamps. Yeah, it looks alright actually. It looks reasonable enough. I'm going to take the exposure off so we can try, and I'm going to be able to, no, I'm not really going to be able to show you this. It's just too dazzlingly bright. Okay, I'll bring the exposure back up then and unscrew this. That looks great, I have to say. Don't try that if you're not sure it's plastic, just in case you end up splintering glass everywhere all over your fingers. So these things are really glued in quite well. Let's see if I can not liberate blood in the process of getting this out. Ugh. Ooh, I think it's using a current regulator. Look at that. Is that the supply in? It is. I think this is using the same approach as Adrian's. Now that's interesting, because if anything, I prefer that approach over the capacitive dropper ones, because although technically speaking the capacitor dropper ones are super efficient, this has the added benefit in such a high wattage lamp that it is going to self-regulate down. Now I've seen what's in these, I'm going to have to buy some more, because that is really interesting. It uses the current regulator chip. In fact, it's probably using virtually identical circuitry to Adrian's. The dollar store ones, turns out there are connections between the dollar stores and pound shops. I'm going to put my screwdriver down here, and I'm going to try and lever the aluminium circuit board out here. There's the capacitor stuffed into those contacts in the back. There is possibly, let's go down and cut that out. $10 ohm resistor in here as the fusible resistor again. Let's check that out. Let's bring the meter back in. So that is stuffing straight into this contact. What's it going to be? What's it going to be? See if we can get a connection onto this. It's a bit footery. I'm not getting a connection onto it, am I? Oh, that's quite high. I kind of want to know what's under that cover now. Is that really a 27 ohm resistor? I mean, 27 is a standard value. Let's rip into that then. This is interesting. This is the first one, I'm pretty sure this is the first one out of Poundland that is using that self-current regulating type circuit. The value of the resistor is red, violet, black. It is 27 ohms. 2, 7 and 0 as a multiplier. There you go. That's interesting. And that is just pushed, if anything, the bare contact, the bare wire is just being pushed through there. But I guess they're not too bothered by that, because the thing is completely double insulated anyway by the housing, whichever one that was out. So the chip, let's take a look at this. We've got the two contacts. I'll bring it back up again. I shall bring it back up and zoom up. And we'll take a look down like this, maybe even brighten the image up a little tad. Well, that didn't work. Excellent. So we've got the little regulator chip. I'm just going to have to use my little magnifying glass here. 474, that's 470k, so that is tied into the connector for the electrolytic capacitor. This one will be the sense resistor. It will be a fairly low value. How accurate is that? 20 ohm? I think that's 20 ohm. And the chip itself is, oh, am I going to be able to read that? You're probably going to be able to read it before I can read it. PT4515 NH, I think that is. I'm pretty sure I recognize that number as just being one of those adjustable current regulator chips. Okay, let's go back down to a comfortable working out here. Focus back down to there. Zoom back out a bit. That is interesting. So we've got 1, 2, 3, 4, 5, 6, 7, 8 LEDs. So each of those is dissipating over a watt. But the question is then, if I was to plug this into the quick test, and I was to leave it running for a while, or into the Hoppy in fact, and leave it running for a while, it should self-regulate down. I'm going to do that. I'll be back in a moment. Okay, it's hooked up, and the first thing to note is if I plug this in and then I fumble about the probes onto it, and this is where I wish I could find my glasses, the dark glasses. I'm going to try and fumble onto one of those LEDs. The voltage across the LEDs is 36 volts. Is that 12 chips in one housing? That's ridiculous. That is a lot of LEDs in one little package. Right, I'm going to angle this down. Right, I'm going to angle it down, and we'll see how long it takes to heat up. If it takes too long, the circuit board is already very hot. But if it takes too long, I'll pause and I'll come back. But we'll monitor the reading, and I'll try not to touch that circuit board because it may be live. It's currently showing the 10 watts. We'll see if it regulates down, and in the meantime, it's time for some candy. And the first bit of candy from Christopher is this Lotus. I didn't even know they did that. It's almost like gingerbread men, but the Lotus caramelized biscuits, but it's Santa with a papal helmet on. Papal hat. Is this like Pope Santa? Does he leave gifts for children and then touch them inappropriately or something? I'm not really sure. But what we have here is the Lotus Santa figure, which tastes, hold on, much like a Lotus biscuit should. How are we doing the temperature? It's getting hotter. The other thing Christopher sent, and I've written his name here to remind me, is Kuberdons. He sent me a few items and a dehumidifier, which is good. It's somewhat bigger than I was expecting for what appears to be a Peltier type one. As you can see, I've been enjoying the Kuberdons original flavour. These things are really nice. If you bite into them, they've got a sweet fruity gel inside. And it's very clear they've been made using that technique that they get a cornstarch mould and they press these pyramid shapes into it and then fill it with the gel and then dust it over the top. It's got that nice crispy cornstarch texture in the gel. How are we doing? Is this thing self-regulating yet? It's not quite there yet. It will be there soon. There's no heat sink to help take the heat away, so it should hopefully regulate down. Oh, there it goes. It's 9.9 now. It's regulating a wee bit. No, it's gone back up again. With these positive temperature coefficient effects, that as it gets hotter, it limits the current more. You often find they waver up and down as they adjust. So at the moment it's saying 9.7, 9.4, 9.74. Right, tell you what. I'm going to pause momentarily and I'll come back in a minute or two after it's had time to totally overheat and start self-regulating. Okay, well, it's not that exciting. It seems to have heated up to the point that it's regulated down to about, it wavers. It's going between 9.5 and 9.2 watts. It's wavering up and down. I think it's reached the equilibrium because the circuit board is in free air here and the heat is basically coming off it. You can feel the heat coming off it. I think it is self-cooling. It wouldn't be doing that. It would probably go down lower if it was in a hot fixture. Certainly, it's got the added advantage of more aluminium in the housing here for cooling. Right, tell you what, I'm so intrigued by this. I am so intrigued. I'm going to do some further tests. That circuit board will be scalding hot now. Oh yes. That is very hot. And I'm going to take a picture of that and I'll be back in a moment. So here's a closer look at the circuit board. The number PT4515, it seemed familiar. If it did seem familiar, you watch my videos a lot. Do you remember this linear sort of like it's a flexible filament inside a glass tube? It had exactly the same current regulator chip, but in this case, it was the sort of little transistory type package 3-pin with tab. In this case, it's also just 3 pins that are being used, but it's an 8-pin package. This pin, this pin, this pin, this pin, and this pin, they're not used. It just uses those 3 pins. I wonder if there's a little thermal pad underneath it. Not sure. The LEDs are just plain outright odd. I reckon, I suppose, you know, give me a second. I'm just going to test this by putting a supply across and seeing what voltage they actually start to glow at. Okay, the LED starts glowing. Can you see it just glowing in my hand there? At about 29.4 volts. And if we do the maths, usually these things start glowing around about 2.4 volts-ish are 2.4 to 2.5. Let's say 29.4 divided by, say, 2.5 gives 11.76. I would say there's 12 chips in this. And the way they're aligned inside, they're quite a long block. Not sure. It looks like two little stacks. If the chip looks like this, then there's two little blocks inside glowing, so I'd guess maybe each of those is 6 chips each. It's a very odd arrangement. I'm guessing that means that perhaps for different countries, different supply voltages, if it was 110 or 120 volts, they could use the same circuit board, but they might use the 6 LED version of the chip instead of what I'm guessing is 12 in this. I'm just going to turn the power supply way down before I turn that back on again and blow the shit out of something when I plug it in. That's better. Okay. So, right, where were we? Yes, let's zoom up in this a bit. So, the supply comes in, live and neutral. They come into these sort of little press-in terminals here, and they go to this bridge rectifier. That converts it from AC to DC. It then goes to a smoothing capacitor, which is pressed into this terminal here. And there's also a 4740's 470,000 ohms, 470k resistor across that for the fast discharge. Also to provide a slight load, so that when you have two-way switching and other arrangements where there's capacitive coupling and switch wires, it will reduce the risk of the LEDs just glowing as they do. Removing that would be interesting. Replacing this with a resistor would also be interesting. That would be very interesting, just to make it into a super low power lamp. That could also all be done from the front of the housing. That might be an worthy experiment for later on, how to convert these into forever lamps that would last for ages. It gets a bit interesting after that. So the positive goes to this LED and then loops to this LED, and then it continues all the way around. But if you put an LED in this position instead, it bypasses the first LED. It loops. Well, it bypasses these two LEDs, but replaces them with a single LED. And the reason for that is it's to adjust the number of LEDs from 1, 2, 3, 4, 5, 6, 7, 8. It adjusts it down to 7. And that might be for countries with a lower voltage supply. It's for fine-tuning the total forward voltage across the LEDs. The current regulator has a sense resistor. The sense resistor is down here. There's two positions for resistors just to possibly allow fine tuning, but in this case they've used a 20 ohm resistor. The chip senses the voltage across that, and it's set to the threshold of 0.6 volts. So 20 ohms at 0.6 volts, I equals the voltage 0.6 divided by the resistance 20 ohms gives 30 milliamps. The capacitor in the back, incidentally, is 4.7 microfarad, 400 volts. I just wrote those on as a reminder. So theoretically, another modification you could make in this, you could desolder this 20 ohm resistor, or in fact, you could just scribe it off. You could take a Dremel and just cut it and solder another resistor across here. And if you doubled that or more, if you, say, for instance, went up to, instead of 20 ohms, you went up to 100 ohms, the current would then theoretically drop to a fifth. That would be about, let's do the maths there. What would that be? I would equal 0.6 divided by 100 ohms. It would be 6 milliamps, the whole circuit. Now, the combined voltage of all these LEDs, because I think I measured that about 36 volts. 36 volts times 8. So the LED voltage is 288 volts. I'm just going to do that down because it's a useful thing to know. 288 volts. At that 30 milliamps, it would be through the thing, it's P equals IV, so that would be current times voltage. So voltage times that 0.03 means the power dissipated by the LEDs is 8.64 watts. That suggests a little bit is being dissipated by this, effectively acting like a resistor in the series. If you reduced it, if you changed it to the 100 ohm resistor, it would be roughly, the voltage across the LEDs would drop slightly, let's say it stays the same, times 0.006 equals it would drop to a 1.7 watt lamp, and that would stay super cool. That would last a very long time. That's an interesting hack. The temptation is there to try it. I wonder what resistors I've got. It would also require the facility to heat this circuit board up to solder that. I shall give that a go later on. I might actually try and do one in situ in a lamp. That would make an interesting video. Although heating it up would be the hard bit. I'd have to work in that. I suppose really you could run the lamp until it was really hot, just with its natural heating, so it heated itself up, and then solder that other resistor in. That would be an interesting experiment. But there we go. That's interesting that it's a good comparison with what Adrian had in his. So Adrian's had probably, it's a different type of chip he has got. It's a different model of chip because it's a different pin out. But it is the same sort of push-in connectors and the same rectifier and resistor, and then the series circuit of LEDs. Very interesting. That's a very novel and interesting twist. I'm going to have to get more of those lamps now because that is a very interesting approach. And I like the fact that the current can be programmed in these either by just replacing the whole regulator circuitry with a resistor, a simple resistor, or changing keeping the regulator circuitry intact and changing that resistor, the sense resistor instead. Very interesting, really neat and interesting lamps. Found a resistor. Circuit board is heating itself up. I think we're ready to make a little modification. Let's go. Solder iron's on. So I'm going to take this resistor here. I'm going to place it on the circuit board. This is where it tombstones. Make sure the power is off. Then heat that. It's hot. It's hot, 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 hot. And the solder's just cured. Oh, that's not a good idea. I should actually have... Oh, that's not working. That's kind of working. And the other side, that's hot, 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 hot. Ow, ow, hot, 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 hot. As you'd expect from a circuit board that has been grilling with LEDs. Can I get rid of this old unwanted resistor now? Is it glued? Ow, that's hot, 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 hot. Ah, get off. Get off. There, it's off. Actually, it's stuck to something else now. Right, okay, that is it. Theoretically, that should now be a 100 ohm resistor in the circuit. The current should drop to about 6 milliamps, which won't be reflected in the current on the display here. But the power will drop to around just under 2 watts. Oh, much dimmer, much dimmer. Oh, it's struggling. It's displaying 4,589 watts. Oh, there it goes. It's crashed. 2.2 watts. That is weird. I'm going to unplug that again. Happy. Yeah, it's down to about 2.3 watts, 2.2. The current, it says 18 milliamps, but that's because it's skewed by the power factor here. But that has regulated down, and this is now running at much lower power. That's interesting because that can be done in situ. If all you do is remove the slightly crumpled cap, you can then make that modification. You can heat it up, unscrew it, and while it's still hot and the aluminium substrate's hot, you can solder those different resistor in. This is a bit ferocious, this image, isn't it? Oh, that's better. Okay, so yeah, that brought it down from the 10 watts to about 2 watts. Interesting, which you'd expect actually, given that I changed a 20 ohm resistor to the 100 ohm resistor. There you go, it can be done. Interesting stuff.